you kidding me? I'm so bad about that. Okay, this is no big deal. You guys can do this one, right? We've got so there's the center. We've got a wrench that's 0.41 centimeters long, so there's my wrench, right? We push on it with 166 newtons, but it's at an angle of 118.3. Okay, good. So that means that the force vector is measured between the lever and the force, so it's got to be a little more than 90, doesn't it? So it's going to push like that, right? So does that make sense? Okay. So that's going to be a little strange, right? But what do you suppose is going to happen if I take, I'm going to ask you a question here. So if I were to move this backwards, this line of force, right? The line of force passes closest to the fulcrum, actually behind the force vector in this case. No big deal, right? So this is that's the lever arm, isn't it? Right? This angle right here was 118.3 degrees. What would that angle right there be? Okay, so the two are supplementary, aren't they? Going back to geometry, so they add up to 180. So what are we going to get? 61.7? Right? Okay, so what do you think I'm going to get if I use 61.7 as the angle? I'm going to get the same thing. I'm going to get the same thing, and here's why. Those of you, so have you guys talked about the unit circle in trig yet, if you're in trig? Mm-hmm. You have started to a little bit? Okay, watch this. I love the unit circle. Unit circle is great. So think about the unit circle here, right? The unit circle starts at 0, and if we do this in degrees, that's 180, right? Now look at this. Here's the angle 61.7, right? Here's going to be the angle 118. Let's make this one blue. Look at this. It's going to be 118.3 is this whole angle that goes all the way around to there. What do you notice about the y components of those two places on the unit circle? Guaranteed. They're the same because how do we use the unit circle to calculate sine and cosine? If I take some point up here, the coordinates, if I call this 61.7, the coordinates of that point on the unit circle are going to be, I'm going to call it theta. Cosine of theta, comma, sine theta. The x-coordinate of any point on the unit circle corresponds to the cosine of that angle, and the y component corresponds to the sine of that angle, right? And so look what we did. We just found these two angles that are symmetrical about the y-axis, right? So either one's going to work. If I put them in a calculator, I promise you I'm going to get the same answer. If I put in sine of 61.7 degrees and sine of 118.3 degrees, same answer, right? Yep.
Can I do number 5 too?
Sure. So this is pretty easy then, right? All we got to do is we're just going to multiply 166 is the force times 0.417 times the sine of either 118.3 or 61.7. Doesn't matter. Whichever one you want to use. Those are the angles formed between the line of force and the lever. Okay? Oh, so okay, I'll pull that one up. Which one is that?
Just like read the question. That's not.
I have one of the diesel.
It says in first gear, low range four-wheel drive, maximum torque is 2,700.
Okay. Yeah. That's kind of a fun one. We'll do that one. Yeah. Is that the challenge? No, number 5? That one. Okay. So how about this guy then? What's this saying? So we've got a 3,050 kilogram diesel truck can exert on the rear axle. The maximum torque it can exert is 174,550 Newton meters. The radius of the tires is 41.03 centimeters. Assuming that the tires do not slip and the transmission components can handle the load, by the way, neither are remotely possible. The truck can theoretically tow a weight of what? Up a hill sloped at a 21.7 degree angle. Okay? So, and by the way, you could easily make a truck that could do this, but you could never build an axle that would hold that. Right. The axle would break. I mean, it'd have to be a really big axle. But you could do this by gearing down a diesel engine. There's no question you could easily produce that kind of torque. So what are we going to do? What's our picture going to look like? I mean, this is the same picture we drew with the tire last time, really, isn't it? Okay, so, right, we know that, here, let me take a picture of this. Oh, hang on. I got to take a roll real quick. If I don't do this, I'll. Kids here, Mavericks here, Scott, Jordan. Okay, that was quick. So. Okay, so what do you think? How are we gonna do this?
Okay, so there's the tires pushing downhill and the ground's pushing uphill.
Right.
I just don't know the mass of the truck.
Okay.
So you need to find the lever arm of the tire, or the, not the lever arm, but the force of the tire, or not?
Right. So what about this? We're going to have to look at this in terms of there's two things. There's going to be how much force are we having to apply to tow this thing up the hill. So let's just take the weight of the truck. Assume that the truck is massless for a second, and that its mass plus the trailer is what it's pulled. Same thing, right? Same thing that it's pulling up the hill. Yep.
Why did you go from kilograms to
where?
Kilograms, so.
Yeah, kilograms for the truck and pounds for the how much weight can you.
Oh, that's being really mean. I shouldn't have done that. I don't know if I even meant to. So we'd have to do a conversion there. Let's just do it in terms of. Yeah, that's pretty mean.
I say we take this question off the side.
That's pretty mean. Yeah. Tell you what I'll do. I'll change it so it'll accept the answer in newtons. How about it? So you don't have to do any conversions. Okay. So, but what are we gonna do? So if we've got this weight, here's the first thing you gotta consider. Right, if we've got this weight of this whole thing that's pushing straight down, we don't have to pull the whole weight up the hill. All we've got to do is pull up the component of gravity along that's parallel to the slope, right? So we'll break the weight, mg, up into two components. We've got mg perpendicular and mg parallel. And that's the only force that we're having to overcome. There's one good hint. We'll finish, start a class. Why don't you guys take the next couple days off? Monday we'll go through this. Okay. All right. You come today?
I don't think so today.
Okay.
But I can't do it right after school, but I can do it later tonight if you have something you want me to do.
I would just do